The following video will introduce you to VisualDOC Matlab interface, which allows user to make use of Matlab to evaluate responses as required during optimization process. VisualDOC opens the Matlab, transfer design variable data to Matlab engine and evaluate responses using user-supplied Matlab code and transfers the value back to VisualDOC. All data transfer is done in memory and the Matlab computational engine is opened and closed only once for each optimization run. Let's start with an example. Consider a rectangular box with two dividers. The objective is to minimize the use of material for making the box, that is, minimize the surface area of the box. Here, design variables are height, width, and depth of the box. It is subjected to constraint that volume of the box should be greater than or equal to 2, where the volume of the box is given by height into width into depth of the box. The constraints on design variables are for height, width, and depth, lower bound is 0 and upper bound is 100. This example is available in VisualDOC Advanced Examples Manual, where detailed steps required to solve the problem by using VisualDOC are given. In this video, I will cover all those steps in detail. Now let's open VisualDOC. Click on the File button on the main menu bar. Select New Project. Select the folder where you want to save the project. Enter the name as Matlab Interface. Push the New Project Database button. Now the first step is to set up the Matlab library path in Path Browser. Click on the Tools button on the main menu bar. Select Path Browser. Now click on Add Matlab Search Path to add the path to Matlab. Browse the location where Matlab is installed. Push the Select Directory button. VisualDOC will automatically add appropriate path for Matlab. It is important to note that 32-bit VisualDOC can only communicate with 32-bit Matlab and 64-bit VisualDOC can only communicate with 64-bit Matlab. Now next step is to create workflow. From component palette, add optimization component. Now click on Matlab component and add it inside optimization component, as this component is used to define the analysis. Now add a stop block. Now click on flowchart components in the model tree panel. Click on automatically connect all models icon. This would connect all the components based on their order in the model tree. Now click on automatically rearrange all models icon. Select Yes. Now I will rename the Matlab component to Matlab Analysis. Right-click on Matlab component. Select Rename Component. Enter the name as Matlab Analysis. Click OK. Next step is to set up the Matlab component. Click on Component Editor tab. Select Matlab Analysis from Model Tree panel. Now enter the variables and responses in the middle panel. It is very important to note that inputs and outputs are transferred to Matlab in the order they are specified in the middle panel. Select Output for area and volume in Input-Output column. Initial value for variables h, w, and d is 1. In the panel on the right, in Matlab Working Directory section, make sure that Use Model Directory option is selected for directory part type. For Matlab.m file, make sure that relative to Matlab Working Directory is selected, as we have saved the VisualDOC model in the same location as that of Matlab.m file. Now click on File icon and select Analyze.m file. This .m file takes three design variables as input, height, width, and depth of a rectangular box, and calculate two responses, surface area and volume of the box. The DVAR vector correspond to the location of design variables in VisualDOC window, and the calculated responses are placed in the RESP vector. In description section, I will provide this Matlab code for reference. Now the next step is to create data transfer to create the data needed for the optimization component. Now go to Data Linker tab. Select Optimization from Model Tree panel. Select Optimization in the middle panel. Make sure that Auto Link checkbox is selected. Now click on Automatically Add Data to Selected Model icon. This would add the corresponding links for the data transfer between optimization and the analysis. Whenever links are added in batch, the entire batch is assigned a specific color to distinguish that batch of links from the others. If you want to change the color of all links to black, click on Reset Color of All Links icon. Next step is to set up the optimization component. Go to Component Editor tab, select Optimization from Model Tree panel. For data area, select the checkbox under Objective column and deselect the checkbox under Constraint column. Select Minimize option from drop-down list in the Goal column. For variables h, w, and d, lower bound is 0 and upper bound is 100. For constraint volume, lower bound is 2. I will be using modified method of feasible direction, which is default gradient based optimization method in VisualDOC. Now I will create two simulation monitors to monitor the best objective and the worst constraint violation. Click on the Simulation Monitors tab. Add two optimization history monitors. Click on the Expand Hierarchy icon below the Flowchart Components panel as well as the List of Monitors panel. Now drag the best objective under Simulation Parameters and drop it on the x1 axis of the first monitor. Similarly, drag the worst constraint under Simulation Parameters and drop it on the x1 axis of the second monitor. To activate the defined monitors, click on Enable All Monitors icon. Now we will test the Matlab component in order to ensure the interaction between Matlab and VisualDOC. Now go to Component Editor tab, select Matlab Analysis from Model Tree panel. Push the test button. VisualDOC will launch the simulation. After successful execution, you will get a message in Standard Messages tab. Now click on Validate icon. Our complete model is valid. Next, click on Run icon to execute optimization. To view the defined monitors, click on Monitors tab in the message area. For both optimization history monitors, x-axis represents number of iterations. For first optimization history monitor, y-axis represents best objective value for each iteration. For second optimization history monitor, y-axis represents worst constraint value for each iteration. It can be seen from the graph that the total number of iterations are 5. There is a constraint violation for iteration 0. The red cross indicates the constraint violation. To check which constraint is violated, go to Post-Processing tab. Select Optimization from Model Tree panel. Click on Generate Summary Report icon. Now scroll down to iteration 0. Thus, constraint on volume is violated. To view the optimum results, go to Component Editor tab. Select Optimization from Model Tree panel. The table displayed in the middle panel has the optimum values in the optimum column. The optimum value for area is 11.99. After 5 iterations, it has been reduced by 5.44%. If you want to restart the simulation from the optimum values, click on Transfer Best Values to Initial Value column button. VisualDOC will transfer the values from optimum column to initial value column. This completes the demo. I hope it has helped you to get familiar with VisualDOC MATLAB interface. If you would like to learn more, I invite you to check other videos about VisualDOC. For additional information, please visit our website at www.vrand.com or email us at visualdoc.support@vrand.com. Thanks for watching.